All right, so today we're going to be talking about finding the four key features of rational functions again. So those four key features are the y-intercept, the x-intercept, the horizontal asymptote, and the vertical asymptote. So just like what we did yesterday, except today we're going to be looking at what happens when maybe sometimes we have a variable in both the numerator and the denominator, all right? And we need to be able to identify the degrees of the polynomials, the degrees of the numerator polynomial, and the degrees of the leading coefficient of the denominator. Or not the leading coefficient, but the degrees of the highest degree of the denominator of the polynomial as well. So just real quick, the category of functions, rational functions, the basic one is 1 over x. And just remember, a rational number is considered a ratio of integers. So like 3/4 would be a rational number, 5/7, 2 over 1 would be a rational number. All right, those are rational integers. Or rational numbers is just a ratio of integers. Rational function is a ratio of polynomials. So we might have one polynomial in the numerator, one polynomial in the denominator. All right, and these are some examples of that situation happening. We can have constants, linears, quadratics, cubics, all in the polynomials or in these rational form. Cortex we talked about as well last unit in polynomial functions, which is a 4th degree polynomial. But today we're just going to look at up to cubic functions. And what we have to be able to do is we have to identify the degree of the numerator versus the degree of the denominator. So like this first example, we have like an x to the first power in that denominator. So that's why the denominator is a degree 1. In the numerator, there's no x in there, so that's a degree 0. So we'd be saying the numerator is degree 0, the denominator is degree 1. For the second example, x plus 1 over x minus 3, so that's like x to the first power plus 1, x to the first power minus 3. So this is a good example of where we'd say, oh, the degree of the numerator is 1, the degree of the denominator is 1 as well. So being able to identify the degree, the highest degree of the numerator and the denominator, very important. Okay. Now, third problem here. We have the first degree polynomial in the numerator. Okay, so even though it's not written down, there's not a number written next to the x, that's a first degree. And the denominator is in standard form, so that's nice, it's easy to tell. This is a third degree polynomial in the denominator. All right, and I'll explain why we're doing this in a minute. It's going to be important when we get down to the next part down here. All right, start talking about that part. And then the last problem here, we have a second degree polynomial in the numerator. It's in standard form. The denominator is in factored form, and we have to remember, in factored form we can just count the x's. There's an x to the first power, x to the first power. There are 2 x's total, so that's degree is 2. All right, so being able to identify the degree of the polynomial when it's in factored form versus when it's in standard form, very important. All right, what we're going to do next is I've got this section here that says we're going to look for patterns recognizing the degree of the numerator when it's less than the degree of the denominator. So right here, we'll say when it's less than. And then down here, we're going to say when the degree of the numerator is equal to the degree of the denominator. All right, those are the two things we're going to be looking at specifically. And we're going to talk about how do we find the vertical asymptote, how do we find the horizontal asymptote, and how do we find the intercepts. What I want you guys to do first is we have these 4 problems down here, 1, 2, 3, and 4. I'm zoomed out on them a little bit. But I want you to use those rational functions. I want you to identify the degree of the numerator and denominator of each one. And then using technology, I want you to graph the function. All right? And then just sketch the quick graph on your paper here. Okay? But go ahead and identify the degree of the numerator, the degree of the denominator. Using Desmos or graphing calculator is not going to tell you that. But so you need to do that by hand. And then go ahead and use technology to sketch a graph. All right? And see if you can properly draw the dashed lines of the asymptotes where you think they're going to be and things like that. And then see if you can identify any patterns of these 4 problems as well. So take a couple minutes and work on those 4 problems right now. Once I have the degrees of the numerator and denominator of these 4 problems labeled, I'm going to go ahead and sketch my graph. So if I were doing this on Desmos, I can see like looks like there's a vertical asymptote at x equals 2, which Desmos is not going to show that asymptote, or even if you're doing it on a graphing calculator, you still have to be able to identify that asymptote on your own. And then the horizontal asymptote looks like it's going to be at about 1, y equals 1. So I would sketch that first. Okay, and then the next part is to go ahead and sketch a quick picture of this. So it looks like we're going to have something that goes like that. And again, we're just doing a sketch. It doesn't need to be super accurate. Just where the line's going to fall on this particular problem. It's going to look something like that. Problem number 2, we're going to have a horizontal asymptote at y equals 0. And then for vertical asymptotes, this one's kind of a weird one because I have an x plus 2 and an x minus 3. Thankfully, it's already in factored form, but it turns out I have 2 vertical asymptotes. One of them is going to be at x equals 3, and the other one's going to be at x equals -2. All right, just like what we did on the warm-up where we were putting these things in factored form. And now this particular problem, it's going to start with something down here. We're going to have some weird line that goes through the middle, like that. And then we're going to have another line that kind of goes like that. And that's kind of what problem 2 is going to look like when we graph it. All right. And again, just a quick sketch of it. And we got our vertical and horizontal asymptotes. It turns out there were 2 vertical asymptotes in this particular problem. Problem number 3 looks like we're going to have a vertical asymptote at x equals -4, a horizontal asymptote at y equals 0. Okay. Now, turns out there aren't any x-intercepts for this one, but when I look for a y-intercept, I end up getting something like a really small negative number. So it's going to show me, a small positive number. It's going to be like 1/16 or something. So it's going to show me that you're going to have a graph that looks something like this, and then another one that's going to be over here somewhere. And I think that's what this one's going to look like, if I remember correctly. I don't have the graphs in front of me or anything. I'm just going off my memory and what I think they look like. So if I'm writing a graph down that doesn't look right to you, let me know. And then the last one, we have a degree 1. We'll sketch the asymptotes first. Looks like there's going to be a vertical asymptote at x equals -4. A horizontal asymptote is going to be at, I think this one was at 3. And again, if we're looking at the graph, hopefully we can identify that. And then we go ahead and figure out our intercepts. So for this problem, it looks like we're going to have an intercept at +1/3, 0. And then, yeah. So it looks like we're going to go something like this and something like that, I think, for our graph for this last problem. All right. And again, it's based on identifying the intercepts and the asymptotes. So let's talk about how to find those. We just used Desmos to graph these ones, or technology. You could use a graphing calculator as well. But how do you find the vertical asymptotes of these equations? So whether it's the degree of the numerator is less than the degree of the denominator, or the degree of the numerator is equal to the degree of the denominator, you're going to do, you're going to set the denominator equal to 0 and solve for x. All right, and that is actually the exact same thing we did yesterday. So I'm going to say same as day 1. That's the same thing we did yesterday. So the denominator equal to 0 and solve for x. It doesn't matter what the degrees of the numerator or the degrees of the denominator tell us. Exact same plan as yesterday. Finding the intercepts. Okay, finding the intercepts. So to find the y-intercept, set x equal to 0. To find the x-intercept, set y equal to 0. I'm going to put x and y in parentheses here. And solve. That is also the same as yesterday. So if we did this yesterday and it made sense how to find the vertical asymptote, how to find the horizontal asymptote, or not the horizontal asymptote, how to find the vertical asymptote and how to find the intercepts, we're doing that exact same thing today. So hopefully that doesn't, hopefully that's not too difficult for us since it's the same idea. The thing that's going to be different today is finding the horizontal asymptote. If we have the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is 0. Or we'll say y equals 0. So if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is 0. There's a degree less for one of them, so it's y equals 0. Here's a degree of the numerator is 0, degree of the denominator is 2, so the horizontal asymptote is 0. All right, that's the first idea. So again, this is different than day 1. And then the last part, the degree of the numerator is equal to the degree of the denominator. Okay, what we end up doing, let's see, what's the best wording for this? I have it written down. Let me pull up my notes here because I want to make sure I like the way I had it written down this morning in first period. So I want to have it written down like that again. But basically, we're going to take the leading coefficients and we are going to write it as a ratio of the leading coefficients. I think that's how I had it written down from earlier today. So let's see if we can find that. Okay. So the ratio of the leading coefficients. There we go. Yeah, so the HA is the ratio of the leading coefficients, which we've recognized leading coefficients before. We did that in mod 3. So now we're just going to write a ratio of the leading coefficient of the numerator and the leading coefficient of the denominator. And that will be how we recognize the horizontal asymptote. Okay. Now, graphing rational functions. Just let's recap real quick on this. We have this equation. In general, this equation y equals ax plus b over cx plus d. Kind of like yesterday where we looked at this y equals a over x minus h plus k. It has these weird variables, but it's still, it all means something. It can all be broken down. So to find key features, to find the y-intercept, we're going to let's do this. Let's do this in yellow. We'll say we're going to plug in 0 for x and solve. That's how we find the y-intercept. The x-intercepts are found when you plug in 0 for y. And solve. Just like what we did yesterday. Plug in 0 for x, find the y-intercept. Plug in 0 for y, find the x-intercept. Vertical asymptote. We're using this equation cx plus d. So like yesterday we used the equation x minus h, and we said that equals 0. And we add h to both sides, we got x equals h. This is how we found the vertical asymptote day 1. Vertical asymptote day 2, same idea. We're going to take cx plus d and set it equal to 0. Set the denominator equal to 0, and now we're just solving for x. Divide both sides by c, x equals negative d over c. All right, so that's what we would put over here. X equals negative d over c. It looks kind of weird because there's weird variables, but it's really not too bad. We're just doing the same thing as yesterday. Set the denominator equal to 0 and solve for x. Okay. And the reason we want to set the denominator equal to 0 is because the function is undefined when that happens. So when the denominator is 0, the function is undefined. And that's why we set it equal to 0. And then the last part, this is the one that's different today. The horizontal asymptote is y equals a over c. And that's from right here. We have the a and the c, the leading coefficients of those values, the a and c of the x values. All right. So you might remember yesterday, day 1, it was just k. Y equals k. That was horizontal asymptote day 1. But today there's not going to be a plus k at the end of the equation. We're just looking at if there's the same degree of the polynomial in the numerator and denominator. So we have to say, let's go ahead and divide a and c. All right, so the vertical asymptote is negative d over c. Negative d over c. The horizontal asymptote is a over c. All right. And then it says, as the value of x gets infinitely large, b and d become infinitely small by comparison, which simplifies this fraction to a over c. That's what that means. We can look at an example of that later, but for right now, we're just saying the leading coefficients, a over c, are what we want to look for that vertical and horizontal asymptote. All right, so let's do one example here. We want to find the y-intercept, want to find the x-intercept, want to find the vertical asymptote, and I want to find the horizontal asymptote. Those are the 4 things I'm always wanting to look for these rational functions. Start with the y-intercept. We're going to plug in 0 for x. So in this particular equation, y equals 2 times 0 plus 1 over 0 minus 3. And now I'm just going to solve for y. 2 times 0 is 0, and then I have 0 minus 3 is negative 3. So y equals negative 1/3. I plugged in 0 for x. I got negative 1/3 for y. I always want to write the y-intercept as an ordered pair. I always want to write the x-intercept as an ordered pair. Very important that I always write those as ordered pairs because an intercept is telling us a physical location on a graph. So important that I do that. All right, just like yesterday, to find the x-intercept. Now I'm going to plug in 0 for y. And I'm going to end up with this 2x plus 1 over x minus 3. And now I have to solve specifically for x. Because I have this x minus 3 in the denominator, I'm going to want to multiply both sides of the equation by x minus 3. And on the left side, I'm going to get x minus 3 times 0. Well, that's just 0. On the right side, the x minus 3's will go away, so I'm going to be left with 2x plus 1. And then I can go ahead and subtract 1 from both sides. I get negative 1 equals 2x. Divide both sides by 2, and I'm going to get x equals negative 1/2. So that's the x value of my x-intercept, but my x-intercept itself is going to be the point negative 1/2 comma 0, because I plugged in 0 for y to find it. All right, vertical asymptote. Let's do that down here. Vertical asymptote, I'm going to take my denominator, x minus 3, and I'm going to set it equal to 0. Add 3 to both sides, I get x equals 3. There's my vertical asymptote. And then last part, the horizontal asymptote, is saying I'm going to look for the a and the c values. The numbers in the very front, in this case, that's 2 divided by 1, or just 2. So y equals 2. And let me show you that horizontal asymptote one more time. Sorry, I'm moving around a lot here. I'm going to zoom out just a little bit. There we go. Y equals 2. And the horizontal asymptote, the whole idea is thinking about end behavior. It's like what's happening on the far end of the graph. If I plug in really, really big numbers for x, like 1,000,000, I'm going to get like, I'm going to essentially have like 2 times 1,000,000 plus a really small number over 1,000,000 minus a really small number. I think it's actually 2x plus 1, sorry. So this is what the thing was talking about, the statement above was talking about, where it says, as the value of x gets infinitely large, like I'm basically having 2,000,000 divided by 1,000,000, which would just simplify it to 2. I mean, it's going to be slightly different. It's going to be 2,000,001 over 999,997, but it's essentially 2. All right. If I were to put that in my calculator, the bigger x values get, the more this thing's going to hone in on the number 2, but it'll never get to that exact number 2. That's where the asymptote comes from. And then the last part I want to do here is go ahead and sketch my graph. So a quick sketch of my graph. I've got my asymptotes that I'll draw first. X equals 3. Y equals 2. And then I want to use those intercepts to help me sketch the line. 0, comma, negative 1/3. Negative 1/2, comma, 0. And now I know, okay, one of my lines is going to be down here in this quadrant of the asymptotes, and that means the other one's going to be up here somewhere. I don't even need to look at the graph on Desmos or anything. I can just identify, if I can identify those intercepts, or I'm sorry, those asymptotes, and I can identify those intercepts, I have enough information to give me a quick sketch of the graph. That's the idea there. Okay, I got 2 more practice problems here, practice A and B. I'm going to give you guys a couple minutes to work on those problems now.